So thank you very much for coming to our optimization seminar. It is my pleasure to introduce the speaker, Professor Alexander Kruger. He has developed a big part of his career in Australia, in Federation University in Malabar, but now he's working in Ho Chi Minh, in Vietnam.
Sorry, I didn't put affiliation.
No.
So your job is a little bit harder. Sorry.
Okay. In any case, we have been talking about, you mentioned that we met for the first time in Reykjavik in 2006, but what really impressed us was the next year in Prague. Because we approached you to ask about a problem we have with some quadratic problem, and you consider that our problem was a practical application, and this made us very proud. We came here telling our mates, oh, we are doing practical applications, because here we are considered to be theoretical. But it was there are several levels of it. So, Professor Kruger is very well known in our community, but for those who don't know him, he has more than 100 papers, has made some fundamental contributions to generalized differentiation, and also fundamental contributions to extremality, which is an important concept in our field, and many other interests in general optimization and variational analysis. So it is our pleasure to have you here, and we are yours.
Okay. Thank you. Thank you very much, Juan, for this nice introduction. Thank you for inviting me here and giving me an opportunity to present here. And I feel being among friends. This is one of the most important things. Extremality comes later. So we have some stability in this room. Sorry, I'm going to talk about something more extremal today. But this is very geometrical, so my talk is going to be also geometrical and very basic. Of course, I'm presenting for different audiences. I'm trying to make a presentation very basic, but we can go deeper if requested. In terms of terminology, in that I'm going to repeat many words which we have already heard in the previous talk. Extremal points will appear. We can talk about stationarity. We can talk about regularity, constraint qualifications, etc. All these things are related. I'm indeed attracting your attention to this important result extremal principle, which is, by the way, by coincidence, is also 45 years old now, like Kajima's definitions mentioned in the previous talk. I will, of course, remind you what this extremal principle is about, but by now, let me just tell that it has proved indeed an important tool for developing optimality conditions, stationarity criteria, and other things. For instance, the co-derivative criterion of metric regularity can be considered as a consequence of this result. And if you take the book of Boris Murdukovich, 2006, and then repeat it in other books, he demonstrates that many results in optimization theory and variational analysis can be deduced from the extremal principle. So this is a very universal tool, but nevertheless, it also has limitations. And since 1980, when it was first formulated, there have been some extensions, some research in related things. And now my co-worker, my former student and me, we are suggesting another extension of the extremal principle covering the conventional result, and which can be applicable in situations which are not covered by the conventional extremal principle. So no affiliation, sorry for that. King comes from Centro University in Vietnam. I come from Ton Duc Thang University in Ho Chi Minh City, Vietnam. Okay, I'm going to talk the same problem. I'm going to talk mostly about this item 3, sequential extremality and sequential extremal principle. But of course, I will remind the conventional extremal principle in item 2, which is an extension of the convex separation theory. So this is the sequence, and in the end, some very trivial illustrations when applied to optimality conditions, sequential optimality conditions, not for extremal or stationary point, but for the case when you have a minimizing sequence, for instance, but it doesn't converge to a point. So such situations appear all the time, and we think with my co-author that such things could also be of importance to get some characterizations, dual characterizations, multiplier rules for this type of situations. And this is a motivation for this extension of the extremal principle. So let me start with convex separation, which is well known, I believe. From the point of view of applications, this hyperplane separating the sets produces or is produced by a non-zero vector, or two vectors going in opposite directions, and it is this vector which we need in applications. This is where multipliers, Lagrange multipliers arise, and you can think of many other applications. When you need dual vectors, you apply separation, and the separation theorem produces you this with this vector. A formal separation theorem. We have two sets which do not. I will use this tool in a slightly different way. It's more convenient. When we have two sets, the interior one of the set doesn't meet the other set, then there must exist a non-zero vector, such that looking at this illustration from the point of view of convex analysis, if we have this common point, then this vector is actually normal to the set A, and the opposite vector is normal to the other set, and this is exactly what is written here. This is a reminder of the definition of the normal common in the sense of convex analysis. And what is important for what is going to come, think of this as two different vectors, two normal vectors, whose sum is zero. This is separation. So I'm going to talk about generalized separation, but the idea is the same, to obtain these two vectors non-zero, such that the sum is zero or almost zero. In terms of applications, in fact, I already talked briefly about this, but I promised geometry. Here it is. You are minimizing a convex function. You know very well, if you have one point of minimum, the gradient, the sub-differential must contain zero. Look, it comes from the separation theory. So consider this epigraph, this lower half plane or half space, they can be separated, and the separation theorem says that there must be non-zero vectors. If you consider the lower set, the only possibility, it must go up. So, for instance, 0, 1 vector. Then, in accordance with the separation theorem, there must be a vector 0, minus 1, which is normal to the epigraph. But if 0, minus 1 is normal to the epigraph, this means exactly that 0 is a subgradient. Of course, so sorry, I'm talking, I'm making things too elementary, probably. Okay. Extremality. Not all problems are convex. What to do? We have this great tool which produces multiplier rules, sum rules, all calculus, sub-differential calculus in the convex case, but not all problems are convex. The replacement was suggested 45 years ago and is now known as the extremal principle. Look at the same illustration, but from a slightly different viewpoint. Non-convex separation. This is still convex at the moment. These two sets can be pushed apart, and the intersection becomes non-empty. And this shift can be arbitrarily small. This is what we, many years ago, decided to call extremality. And the great advantage of this, the sets don't have to be convex. Other definitions, the same situation. They can be pushed apart, they can be pushed apart. These are examples of extremal systems. But we need these two vectors working in opposite directions, normal vectors. Here everything was clear. Here, more or less clear. You can still think about a normal vector to this set B. What about this? Is it possible? The answer is yes, but you need to think about normal vectors in some different way. You need other normal vectors. So such vectors exist in all these situations, and this is actually the essence of the extremal principle. Like separation theorem, it guarantees the existence of such vectors. But how to interpret this vector? So, yes, it is in a sense normal to the set B, and I will try to explain in which sense. This is the formal definition of extremality, 1980, 45 years ago. Extremality means at a point. For any epsilon, you can find the vectors arbitrarily small, such that when you apply these vectors to each of the sets, you are basically pushing the sets apart, and the intersection becomes empty in a neighborhood of the given point. And here I'm also using some small trick. I'm repeating the terminology from the previous talk. The trick is here. Rho is allowed to be plus infinity. So in one definition, I'm combining what we used to call local extremality and global extremality. Now I just talk about extremality, but I am allowing rho to be equal plus infinity. And in the simplest case, you can just think of rho being equal plus infinity, and this set disappears in the whole space. But otherwise, like in optimization, we talk about local conditions, then we need this rho. Not necessarily equal to plus infinity. The tools used here are free shared normals. This is the definition. Unlike the convex normal cone, it's a local constant. X goes to its bar. So the definition is basically the same, like in the convex case, but it allows some curvature. If the set is convex, it will reduce to the same definition of normal cone in the sense of convex analysis. So this normal cone can be interpreted for these two sets in the natural way. Convex case, exactly the same. This case, this is exactly where this lim sup operation, local operation, allows to consider this vector, and locally it is more or less the same, like with differentiation. So smooth surface, and under the microscope you can think about the surface being flat. So same, but this situation is already different. The normal cone is 0, trivial normal cone, which is not very nice, because if you recall what I've been talking about, we need non-zero vectors, we need non-zero normal vectors, and a failure in this situation. Not a complete failure, and I'm going to demonstrate this. It is still possible to talk about some kind of generalized separation, and it is still possible to find non-zero normal vectors even in this situation, but in some extended sense. I'm repeating this definition. I'm going to repeat it again for the third time, so you will remember it forever.
Finally, you will learn.
I'm an expert. The extremal principle, the dual characterization, is proved for the case of an acyclic space. I'm not going to go deep into the theory of functional spaces. I just people who work or use occasionally Frichet normal cones, Frichet derivatives, Frichet subdifferentials know very well that these constructions work in acyclic spaces, or in particular in finite dimensional spaces. Every finite dimension and every reflex bounded space is acyclic. The sets are assumed to be closed. This is already a hint that we are going to use another tool, a comparison matrix. So we need closeness, closing continuity. Anyway, this is the theory. So the conventional extremal principle, which is 45 years old, says that in this situation, we can find some points in these given sets arbitrarily close to the given point, and Frichet normals. So Frichet normals are computed not at a given point. You remember this illustration where this normal cone was trivial. But this theorem guarantees the existence of some point arbitrarily close to the given point. And normals computed at this point such that they are not zero, and their sum is almost zero. So this is an example of a fuzzy result. We cannot guarantee the exact zero. We cannot guarantee that we can take the given point, but approximately we get what we want. So this is the conventional extremal principle. I provide two references here. This is the original statement where the original definition comes from. In 1980, we knew nothing about acyclic spaces. So the result here is a bit weaker. It was formulated for spaces admitting an equivalent Frichet differentiable normal. Frichet differentiable away from zero. and not for free share normal cones, but for sets of epsilon free share normals. Some slightly bigger set. This form was published in 1996, 16 years later, thanks to a famous result by Marian Fabian, who actually introduced us into Aspen spaces. Now everything is pretty clear, but it was not clear at all in 1980. Okay. And by the way, the name extremal principle also appeared here. In 1980, in our first paper, we call it generalized Euler equation. The terminology borrowed from the very famous, at that time, paper by Dumaritsky and Milutin. Probably you've never heard these names, but these were great guys who contributed a lot to this theory, to optimization theory, mostly optimal control, but not only.
But I remember Dumaritsky optimality conditions.
Normally, people refer to two names always because they worked together, and in many, if you Google Marcinet or try Marcinet, you will find many publications where authors mention Dumaritsky, Milutin, formalism. So they developed quite a nice general model, and they also produced something similar using convex analysis tools, and they call an equation, because they actually use zero here, they call it Euler equation. So we borrow the terminology from that. And but now nobody remembers Dumaritsky and Milutin, and Euler equation is only in calculus operations. And these two guys came up with this name extremal principle, and now everybody calls it extremal principle, including myself. The tools used in the proof are these two key results of variational analysis. I already mentioned Marian Fabian, who proved free share subdifferential sum rule. And this is the key result. Now it is an easy exercise on application of these two results, but the original proofs were huge and scary. Now everything is easy, everything is simple. Okay, this is the history. So what else? This extremal principle is a nice tool, it works. You can produce optimality conditions, calculus results, whatever. Optimality conditions, we already had this illustration. And now if you use this extremal principle, the sets don't get to be convex. Sorry for this very, I was unable to come up with some better illustration, but the function is not convex. And it works the same way. This normal goes here, this normal goes here, and zero is a subgradient in some sense of this function above. And once again, this is a simple illustration, but Lagrange multipliers are here. Subdifferential sum rules are here. And the first thing actually we did around 1980 is proving various multiplier rules for standard optimization problems, for vector optimization problems, for minimax optimization problems. So all these things were published around 1980. But there appeared some situations which are not covered. A simple situation like this one, and the situation is convex. We have this exponential function, lower half space. you can observe some kind of extremality. Or in fact, this is a convex case. These sets can be separated. But where are the multipliers? So, in fact, it was not entirely our idea. Very recently started appearing some publications treating optimization at infinity. This particular paper is about subdifferentials at infinity, but this guy, Ton Duc Thang, and his courses, he publishes with different courses. He's now interested in different conditions of infinity, optimality conditions, also co-derivatives conditions of infinity, etc. As you can easily guess, he comes from Vietnam. I listened to his presentations at a couple of conferences, and I started asking him questions. What is infinity? Even in this simple case, we can talk about plus infinity and minus infinity. And the behavior of the function at minus infinity is completely different from this one. So this way, I actually pushed him to producing some classifications of his infinities in more general situations. And I got myself interested in, he didn't know about the extremal principle, by the way. We discussed with him the situation, and we got interested, and he got interested in producing or finding something as an analog, as a replacement or extension of the extremal principle when applied to this type of problems. And especially my course, I'm going to do who is my former student, by the way. He got interested in this stuff, and we started producing something. This is where this story originated. By the way, these guys also published in top journals. I'm not flying that high. I normally choose more modest journals. Anyway, I'm gradually coming to this item 3, sequential extremality and sequential extremal principle. We succeeded in finding an extension of the extremal principle covering situations like on the previous slide. The set time. So you are already prepared for the test, which is coming in a few minutes. The key point here, we were assuming the existence of common point, which is not the case in this last demonstration. So instead of this given fixed point, now I'm going to assume the existence of two sequences in each of the sets, such that the difference goes to 0, which basically means that the distance between the sets is 0. But I'm assuming that these sequences are given, just like the point was given here. So we can separately treat plus infinity sequences going to the right, or sequences going to the left, or whatever in infinite dimensions, for instance. So this is a replacement to the point. Okay. The new definition. We say that this pair is extremal at these sequences, and there is this more or less the same. There exists a row which can be plus infinity in particular, such that for any epsilon, just like here, a new thing is here. We can find k as large as we wish. There must be a k as large as we wish. if we are assuming epsilon to be small, then epsilon to the power minus 1 is large. And we guarantee this definition assumes that there exists such a k, such that here instead of a and b, we are taking a minus ak and b minus bk. So these both sets contain 0. And we are in the previous situation. Just x bar is 0. So instead of the neighborhood b row of x bar, we could just row b, which is a unit ball. In the particular case, in particular, a k can be equal to bk and equal to x bar, 1 point. Then this definition becomes reasonable. So this is an extension of the conventional definition of maximality. By the way, in terms of terminology, we used to call this point maximal point. Again, the terminology used in the previous talk, but for slightly different purpose. Now, the statement, the sequential extremal principle, the assumptions, not necessarily Asplund, can be general part space, which is not a big advancement. The original extremal principle can also be reformulated for general finite spaces. And the theorem says that if the system is extremal at these given sequences, then again for any epsilon we can find k as large as we wish. We can find point close not to x bar, there is no x bar here, but close to a k corresponding to this k. B close to bk, and then we compute normal cones to A at this point, normal cone to B, such that the same result is here. But notice here I'm using Clark normal cone. Not Richet, but Clark. Because we are in the general finite space. And we have item 2 here. If x is Asplund, then instead of nk, we can use n. And this part, the second part, covers the conventional extremal principle. Why Clark? Because Richet doesn't work in general finite spaces. It doesn't have any Clark. We are still using the same 2 items, a conventional principle and some rule. We don't have some rule for Richet, we have it for Clark. Or you can take your, for instance, some differentials, normal cones, any nice normal cones which possess sufficiently good calculus. That's it. So this is the main result. In the example which we have something like this. We can identify, this theorem says that we can find points with arbitrarily large k, such that the vectors, normal vectors exist, non-zero, but the sum is becoming more and more zero, close to zero. Of course, this is a convex situation, but even in the convex situation, we get something. And we can produce some Lagrange multipliers this way, approximate Lagrange multipliers. And by the way, probably I should have mentioned this earlier. Unlike the classical separation theorem, we don't have this assumption that one of the sets has non-empty integral. They can have empty integral. We don't have this restriction. Optimality condition. Very simplified example. Of course, don't expect something dramatic here. Assume that we have this oversimplified problem, minimizing a single function subject to a single geometric constraint. The space is bounded, the set is closed, the function is lower semi-continuous, and we're assuming that the infimum is finite. Applying the sequential extremal principle, we arrive at this theorem for any minimizing sequence. Again, for an epsilon, you can find a k arbitrarily large, you can find points arbitrarily close. Note here, we work in x times r. We are applying extremal principle to epigraphs. So we work in x times r. So there is one more component, which in general, which if we don't impose any additional assumption, doesn't have to coincide with the value of the function at this point. Then we have normals, either Clark or free share, if we are in the aspirant space, such that we have this almost zero. This is a multiplier rule. And this non-triviality condition, of course, including this normal to the epigram. But the statement is not attractive. We want some differentials, not normal columns at some points. But by the way, of course, if mu1 is not equal to f of x1, but greater, then x1 star is 0. So we have a horizontal norm. This is a singular case. If we want to exclude the singular case, we need to assume something. And the simplest way, assume that the function is Lipschitz continuous. There are weaker assumptions. But just for illustration, if you assume that the function is Lipschitz continuous, at least near a tail of this given sequence, not everywhere, just at the very end of the sequence, then this mu1 will be equal to f of x1. So instead of saying that mu1 is less than infimum plus epsilon, f of x1 is less than that. So it is almost infimum up to epsilon. And we have this multiplier rule. And of course, again, the second part, if the space is epsilon, we don't need Clark. Cliche is operator. So I think we're almost done. I was too quick.
No, it's perfect. It's perfect.
But I noticed that I have a few minutes. Let me say, let me get back a little bit and say something about Seminario. I want to. This is, of course, the most important slide in my presentation, but this is not what I wanted to show at this stage. Just a definition. I want to go to the definition. We have two definitions on one screen, which is very good. The conventional definition of extremality and this extended sequential definition of extremality. And I also had some illustrations, minimizing some function, and we have the point where the function attains its minimal value, or minimizing sequence. Just like standard optimization problems, we can talk instead of optimality. So this extremal point corresponds to optimality. We can talk about stationary points. They don't have to be optimal. So this definition and this definition have extensions. I had many years ago definitions of stationary system and approximately stationary system. Here and here. So weaker assumptions, which still guarantee the same conclusions. Just like in optimization theory, we know if a point of minimum, 0 is a subgradient. But it is also true for stationary points. The same situation here. What is interesting for this situation, if we take this weakest definition of stationarity, which we now call approximate stationarity, we actually in Aspen spaces obtain necessary and sufficient conditions. Here, all the theorems give necessary conditions. If extremality, then some multiply or generalized separation. Okay. False. If you take this weakest definition, you get even only in Aspen spaces. So you get complete duality. Complete duality is nice by itself, but if you reverse this definition and talk about the absence of approximate stationarity, you immediately obtain dual characterization of the absence of approximate stationarity, which is also nice. But what is absence of approximate stationarity? This is something which is now very widely known as transversality. When sets have a good intersection. Montgomery promotes simplification, for instance, is an example. Another example is metric regularity. We know Montgomery promotes is metric regularity of 7 metrics. So metric regularity is an interpretation of the absence of abstract stationarity, and the conclusion of the extremal principle, if you reverse these conditions, gives you what is known as co-derivative criterion of metric regularity. So this stuff is here, but it is broad. First, because now it is sequential, so we can talk about sequential metric regularity, we can talk about sequential transversality, and partially we talk about such things, but we are hopefully going to talk about these things further, and we have some plans of producing some publication, because the results are clear to us. It's a matter of sitting down and writing these things. So, in fact, we can go from here in some more directions, which we now already know, and we can produce some other results along these directions as well. Now, let me approach the final slide. But before the final slide, there is this second last slide with the history of all these things. The extremal principle under the name Euler equation, as I already explained to you, was published 45 years ago in a language which probably not everybody in this room knows sufficiently well. It was a 3-page note which has been widely cited. I think by now close to 200 citations. I'm not sure that everybody who cited actually read the paper. Because occasionally I find crazy things attributed to this paper, which were not there. A more detailed exposition of this theory, 67 pages, appeared next year, and it was the main part of my PhD thesis. At that time, also mentioned. as you could expect. This is where the name external principle appeared. And by the way, this is also an important paper from the point of view that it was also shown here that the external principle in the form which I presented here is actually equivalent to the Aspman's property of the space. So it cannot be extended using free set normal cones beyond Aspman spaces. This is the paper which produced some motivation for us. In fact, not the paper, but the talks which Ton Duc Thang presented at some conferences. I must confess that I haven't read the full paper yet, but I know more or less what is in this paper. They actually published 3 or 4 papers this year. I think this year some are in preprints at the moment. This group is very productive. All Vietnamese people are very productive. They work hard, and you ask a question today, tomorrow morning you will get an answer. They work at night. This is our paper, which is the basis of our presentation. Currently it is a preprint. Yesterday or the day before yesterday I got the first reviews, and I'm hoping that the paper is going to be published soon. And now the last slide. Thank you for your attention. And thanks also to the online participants for joining us today remotely. Thank you.
Okay, are there any questions?
Well, I feel certain curiosity by this concept of subvariance at infinity. More or less, which is the idea behind? Subvariance.
You are asking
Yes.
about.
Yes, I see your example.
Yes, this paper.
Okay, this is easy just to give some, how do you say, rough idea about, because
in my
opinion is something related to a point. How do you say that? Some differential in one point, it's clear.
So the idea behind this paper was to basically to do what you just said, to add an artificial point to the space,
yes.
infinite point, and treat it as a usual point.
But uses kind of geometry?
Basically, the same idea, the same geometrical idea which I used here to approach infinity.
But not projective geometry. It's not the idea behind projective geometry, not points at infinity. No.
I'm not familiar with projective geometry.
Yes.
So geometrically, the idea was clear, and from the point of view of applications and optimization, indeed, we talk about minimizing sequences, even when the minimum doesn't exist.
Yes.
And maybe these minimizing sequences are also of interest from the point of view of characterization.
Minimizing sequences is a very straightforward concept, but suddenly at infinity point is what surprising to me. Because which is the infinity point here, your example here? Which is? Okay. Yeah. Okay.
So somehow, if you have a minimizing sequence conversion to the or diversion, diversion, say to infinity, then zero belongs to the differential
at infinity. And this is exactly what these Vietnamese guys are doing. They introduce this artificial point, and then they formulate conditions. They define subdifferential at infinity.
Yeah.
They define coderivatives at infinity, partial, because they want if two components, one component to go to infinity, but the other component not to go to infinity. So we came up with a more general model, just some sequences. We don't need artificial infinity
But it's
points.
nothing to see with the infinite subdifferential. Infinite subdifferential, the book of Rockefeller, Wells, etc. is when you consider the normal, so any subvariant in convection analysis is related to one vector minus one.
Yeah.
And instead of minus one, you have zero. This is the
Singular.
singular
Yep.
subdifferential. And they represent is nothing.
It is partially related. It partially appears in this first multiplier rule, which I formulated, where I allowed a point to be not exactly the value of the function. I talk about possibly horizontal normal.
Yes, for example.
This is covered, but it was covered actually by the conventional extremal principle as well. We don't have to go to infinity. So these are two different things.
Yes.
Of course, they somehow meet occasionally somewhere, but these are different things.
Thank you.
So I explained that I came into this accidentally. After listening to two talks, one of the points of enjoyment is, so, you know, I like Alicante. I like Alicante, but I also like Dalat in Vietnam. This is where this guy whom I mentioned lives. And for those who are not frequent visitors in Vietnam, let me say that Dalat is a resort in the mountains, because it's very hot in Vietnam, especially in the south of Vietnam. It's very hot. But Dalat is a little bit in the mountains, and it was built by the French at some stage as a summer resort. They have a small university there, and this guy works there. So he invited me and Kim to visit his university, and we liked the place. I liked the place very much, and I decided to contribute. Okay.
Thank you very much.
Any questions from online? Yes. Okay. Thank you very much.
Thank you.